Hi everybody and welcome to part 12 of the Bravo project. Today we continue our discussion of our UART module. In the previous video we looked at the transmit side or TX side. In this video we're going to focus on the RX side of the story. Now the RX side will be a little bit more complicated, and the reason being is that we are actually receiving data on Bravo, and therefore we have to detect the start bit, the length of the data, and the stop bit, and so on. So it's quite exciting. Let's get started by going through the circle logic, and after that we're going to go ahead and test the module.
All right, so let's have a look at the RX module circuit and see how it works. Just like the previous video that we looked at a couple of slides, we're going to go through these slides here again, but I'm not going to obviously go through the same material. I'm just going to point out a couple of points which are important for our RX module. Now, in TX module, we were trying to send some data from Bravo side to the PC side. And if you have watched the previous video, we went into details of how that happens. In this video, we are talking about the RX modules. So we are basically trying to send data from the PC side and receive it on the Bravo side. We are kind of doing the opposite of what we were doing in the TX module. There are really a lot of similarities between the two, and essentially we're talking about the same circuit, right? We're talking about UART. However, if you notice here, this time we are actually trying to get the data from a serial line, specifically from our RX line, from Bravo's perspective, and that data needs to be converted back to parallel. So that means that we actually have to look at RX line this time and get that data bit by bit from that line and convert it back to parallel. So this is our first challenge. The second challenge will be the same. Essentially, we have to match the speed, obviously, and we talked about that in detail in the previous video, that how we could actually match the speed between the PC and Bravo. And finally, we have the structure and format of the data. Again, we talked about that in details in the previous video. However, the difference here is that we are actually on the receiving side of the story, and therefore we have to detect a couple of more things. So, and when we were on the TX side and we were basically just sending out data, if you remember, I explained that we need to actually set a start bit, basically bring the line from idle to low, and then after that we could, send the data bit by bit on the line. Now here, because we are on the receiving side, we actually need to somehow detect that start bit on our side. So when the PC is actually sending the data, we should be able to detect the start bit, and then right after the start bit, we should be able basically to pick up the data. Therefore, the RX module will be slightly more complicated than the TX module, and the reason being is that we actually need a circuit to detect this low bit or the start bit, and also after that we need to actually count for a specific number of bits so that we could cover all the 8 data bits that are coming to Bravo. That's really all I wanted to cover and talk about the differences between the RX and TX module. Now let's go back to the circuit and see what's going on. So as you can see, we have a slightly bigger circuit here, and it looks like there are more chips involved. So let me just give you a very high overview of the circuit, and then we go into details and talk about how each part works. So the circuit consists of 3 main parts. And the first part is another 74HC161 chip here, which is just basically a clock divider. And again, we talked about that in details, how the clock is divided from the original clock, and it's going to be divided by 16, just because we need to match the speeds for the UART communication, or basically match the baud rate. So this chip here is really dividing the clock for us. Now, for the serial to parallel conversion here, we are using a set of 74HC164, which are basically doing a serial in and parallel out for us here. These chips are doing exactly the opposite of what 74HC165 were doing for us in the TX module. In that module, the data was coming as parallel data, and then it was going out as serial. However, here, remember, we are on the receive side, so all the data actually is coming from this RX line on one line as a serial line, and we have to take that data and convert it back to parallel data, as you can see. And these two chips are doing exactly the same thing for us. However, the output of those chips are not going directly on our bus. We just have a transceiver here, our beloved 74HC245 transceiver that we have been using it in different modules in this computer. We have a chip here that actually takes the output of those chips and store them as a buffer. And whenever we need to put that data back on the bus, we bring pin number 19 low, and that's going to do it. So this is the second part of the circuit, which is serial in, parallel out part of the circuit. Well, the last part of the circuit is really a chip here along with a couple of NAND gates that could help us in detecting the start bit. And this is quite important because this little circuit here could not only detect that start bit, but also could run the whole RX module for a specific number of clock pulses so that that data that are sent could be received here and basically converted to parallel. So this part 3, is really a 74HC193 chip plus a couple of NAND gates that we're going to talk about that. All right, so now that I gave you a big picture of the whole circuit and the fact that we have 3 main sections, let's go to each of those sections and talk about them and see how it works. Now, we're going to start with the easiest one, and that's going to be our clock divider. All right, so the only difference between this circuit and the circuit in the TX module is that here we are actually using the inverted clock as the input to this clock divider. And there is a reason for that, and essentially it really all goes back to the timing between different signals in this whole circuit. So as you can see, the clock is actually connected to an AND gate here, and essentially it's just inverting the clock for us. However, the clock is still running at the same speed. So when the clocks come into our clock divider, again, just like the previous circuit, we are not inputting anything from input side. We are really just pulsing this chip to count. And basically what we get in the output of this chip, which is the most significant bit, is the clock rate, which is basically 1/16 of the clock rate that is coming into the chip. So this is just a clock divider, takes the original clock divided by 16 and outputting it on pin number 11. Now let's go to the serial to parallel inverter. Let's first talk about a couple of pins here that we have. So we have a DSA, DSB, and the clock pin, and a master reset. I mean, first of all, we are not resetting those chips in any situation. So the master reset on both of those chips are, tied directly or permanently to high. And that means basically we are not resetting those chips. So those chips will be active all the time. All right, so as you can see, we have actually 2 serial inputs into those chips. However, these serial inputs are internally AND gated, meaning they are actually going to an AND gate inside the chip. So since we are just coming from one serial link here, we could tie the other one to high, and that causes that whatever signal coming on the DSA will basically be shifted to the outputs, and this way we could just tie the DSP to high and basically ignore that. We will be using only one serial input here. And of course, just like the previous circuits, these 2 chips are cascaded to each other, which we're going to get into that in a minute. But imagine that the data is coming in a serial input line, and with each clock pulse that we're receiving on the clock pin, pin number 8 here, which is actually the output of our clock divider, we will be shifting the data from serial to the parallel lines. So when the first bit is actually receiving, we shift it to Q0. And then when the next one coming in, the Q0 value will be shifted to Q1. And this new value on the serial line will be replacing that on the Q0. and so on. So with each bit of data, we're just going to put it on Q0 and shift one bit to the right. So now, if you think about it, we have a low signal which comes in, and after that, we're going to have 8 bits of data, and finally, we're going to have a 1 high bit of the stop bit, right? Remember from the order of the bits. Therefore, if you actually shift those bits one by one, what will happen is that the basically first bit of the data is going to end up on Q0 of the second chip, because again, the shifting is going to happen from left to right. But if you remember, we also have a stop bit, which is the last bit, and it's a high bit. And that high bit is actually going to land on Q0. And that's interesting because, as you can see, Q0 is not connected to actually our transceiver. It's not connected to our output. Therefore, we just kind of ignore that. And that is normal. That is expected. We really don't care about that high bit at the end of the data, because this is not part of the data. The data is really 8 bits, and one of the bits are going to land on the chip on the right-hand side. However, if you look at them, the output of those chips are actually connected to the input of our transceiver. And again, if you look at it, the Q0 here is actually connected to the least significant bit, which is B0 on our transceiver. And again, the rest of the bits are connected to the corresponding pin on our transceiver. So that's basically how it works. Data come in as serial and will be shifted on those pins. And eventually, this data is going to show up on our transceiver. I mean, this chip doesn't have any output control. So as soon as the data is actually shifted, it's going to be already on the input of this transceiver. Now, the transceiver, it's quite simple. It just have a pin, which, tells us the direction of the data. And if you want to actually the direction of the data to be from B side to the A side, which is the case here, we just need to tie this pin low. As you can see, it's tied low. And then finally, we have one pin which controls the output, which whenever we need to put the output of this chip on the bus, we need just to bring pin number 19 low, and that's going to take care of it. So I hope that the serial to parallel transition here is clear how it's happening. However, we still need to look at a couple more things here in the circuit. Since this part of the circuit is actually going through multiple transitions on the state, I actually decided to create a couple of more, let's say, circuits here with some markings on them, so that it will be easier for us to go through it and understand exactly what is happening in the circuit. Therefore, I've copied the same circuit here into a new page, and I put some markings for the signals. And as I said, I'm going to go through 3 different states here because we'll be transitioning from one state to another, so it will be really difficult if you don't have those markings on the screen. So I try to basically follow those low and high signals and describe exactly what is happening here. All right, so let's start with the first stage, which I called it stage 1, and this is basically idle state. So in idle state, as we talked about it in the slides in the previous video, the TX, or in a sense RX line, are held high, right? So we talked about it that by standard, UART always keeps that line high when there is no communication over it. So RX line is high at this point. And also our control signal, which we call it TO signal in the circuit, and it's here at the bottom, is kept low. And this is the signal, just like we had the TI signal in the previous module that we had to bring it high in order to send data. Here we have another signal, which is called TO, and we need to bring that high when we want to actually receive data. This is basically our control signal for RX module. So by default, in idle situation, this signal is actually kept low. All right, so let's see what will happen. So RX line is high. So what will happen is that the RX line comes into a NAND gate here. And let's assume that the other pin to that NAND gate is actually low. Okay, let's just assume for now, because we're going to get to that. And it's actually like a circle. We had to go through a whole circuit to come back to here. But for now, just imagine that that signal is low. Now, if RX is high and this signal is low, the output of this NAND gate here will be high, right? So when this output is high, again, we have kind of combined that with another signal here, and that let's assume for now that this signal is also low. So essentially, we have an AND gate here that will be outputting low for now. All right, so high and low coming into an AND gate, and the output is low. So when the output is actually low, and that output is going directly to the master reset of our clock divider, that means that, and remember that the master reset on these chips are active low. So in fact, it means that we are resetting that chip. We are not actually counting on our clock divider. And regardless of what we receive on the clock pin, this chip will not be counting, and therefore there will be no output on pin 11. So in a sense, this chip is shut down for now. All right, in ideal state, our clock divider is not counting. And therefore, when this guy is not counting, we have another chip here, which is 74HC193, which is a very interesting chip. This chip is actually a presettable count down or count up chip. And it's an interesting chip because it could either count down for us or it could actually count up. Most of the binary counters that we have seen so far in the previous circuits are count up circuits, meaning that we set a value on the input lines, and when we pulse the chip, it's going to count up from whatever value you set to the maximum value that it could count. However, here we actually have a count down chip. What does it mean? It means basically you could set a value on the input side, and then once you set the value, when you pulse the chip, it starts counting down from that value until it reaches 0. However, during that countdown, basically as soon as you set the value on the input, until it reaches the lowest value, it keeps one of the lines, which called the TCD, or the count down line, high all the time. So let's go back to that one more time. When we have an input, and that input is set to a specific value, and we pulse the chip will be counting down from that value to 0. However, for the duration of that count, it keeps the TCD line, or the count down line, high. All right? So now let's have a quick look at the other pins. Now we have a master reset pin, which is tied to ground, and this actually requires an active high to be reset. Therefore, this chip is not resetted. However, it requires a clock pulse basically to come into the chip, which currently is not counting. It comes from the clock divider, as you can see. We talked about that, right? This is resetting, therefore no clock pulse is coming here. And also, if you look at the CPU, this basically the count up basically pin, which tied to high because we are not counting up. We're just using the other, which is the CPD count down basically pin to do a countdown. Now, an interesting thing that you can see on the chip is that on the input side, we are actually tying some of the pins on purpose to high. So D0 is the least significant bit, and D3 is the most significant bit. However, as you can see, D1 and D3 are actually tied to high. So that means we are actually setting value of 10, exactly 10, on the input side of this chip as an initial value to count down. We set the value of 10. However, the PL, or parallel line on this chip, is set to high in the ideal state. And that means that the chip is actually not reading the input. We just permanently set it to 10, and whenever this chip becomes active and basically this pin goes low, then it's going to read that 10 into the chip and start counting. However, at this point in ideal state, we don't have a clock pulse, and the PL line is actually set to high. That's an active low pin. Therefore, the chip is really not counting. It doesn't do anything. However, just remember that value of 10, and this is important because we're going to come back to that in a minute. And also, if you look at the TCD line, which is the output of this chip, well, the outputs are from Q0 to Q3, but this chips, again, as I said, they have two other outputs, which are the TCU and TCD. which gonna go high or in case of count down or count up. So if you actually set the pin to count up, and once you reach the maximum number, then the TCU is gonna go up. Essentially, these are the carry out pins on this chip. However, when you are doing a count down, during the count, the TCD will be kept high. Once it's reached, 0, it's gonna set to low. For now, because, let's assume that we are at value of 0, we are not reading anything from inputs, so this line is actually set to low in the ideal state. And now let's see what will happen. So this line goes up, and this is one of the mystery lines that we had previously. And I said, imagine that this is low, and as you can see, currently it is low. So I know that the circuit is a little bit more complex, but let's continue our journey in this circuit and see what will happen in ideal state. So if this line is low, that comes to 2 inputs on the same NAND gate, and that means that our NAND gate is actually outputting a high, right? So the output of this NAND gate is high, and as I mentioned, we still have the TO line low, so we are not setting the circuit to receive data. Therefore, the TO line is low, so if one is high, the other one is low. This NAND gate, again here, outputting high, and when it's outputting high, as you can see, this is also connected to the output of our transceiver. Therefore, transceiver is not outputting anything on the bus. And again, the both signals when are high in this NAND gate, the output will be low. And regardless, of course, the clock signal coming to another NAND gate here, and regardless of actually the status of this clock, because one of the legs are low, the output of this final NAND gate is actually high. Now, just follow, the low and highs, and just bear with me for a couple of minutes. This circuit will be quite interesting in a couple of minutes. However, the final output is high here, and that high actually comes to another NAND gate, and this NAND gate, as you can see, is crossed. It's more like a like a flip-flop circuit. So as you can see, it comes as a high, and since if you remember, we talked about that actually the signal is high, and since this is actually going to loop back to the same NAND gate, so we have high and high as the input of this NAND gate, and therefore there will be a low coming again to the beginning, and that's exactly this signal that we talked about at the beginning when I said imagine for now that this is a low signal, and as you can see, we get a low signal here. So this is quite logical. In ideal state, these are really the status of each of those pins. Now let's move on to next stage, and let's see what will happen. So if you go actually to stage 2, and stage 2 is where we actually set the TO line high. And when we want to receive data, essentially we gotta have a signal, right? And that's the signal that we talked about that. And let's say that we are ready to receive the data, and we just bring that TO signal high. So let's see what will happen. So let's this time start from here. So this signal was high previously, and we essentially are bringing the TO high. So high goes into one NAND gate, and basically that's going to give us a low signal. Remember, for now, just ignore those arrows. The state that we are in is actually low at this point. I have those arrows for another talk, which we're going to get into in a minute. Basically, those are transitioning in a minute, but for now, the output of this will be low. So what does it mean? That means that we are actually outputting the content of our transceiver on the bus. We also will be setting the output of that NAND gate to high. And on the rising edge of the clock this time, we're going to have a high, which basically leads to a low signal on the last NAND gate here at the bottom. So that signal was previously high, now it's actually low. So if this becomes low, then obviously the circuit is going to change, because this time we had a high and a low combined, and therefore we're going to have actually a high signal output here. So the high signal goes to our first NAND gate here, And since the RX line is high, both of those lines will be high, right? So when this happens, the output of our first NAND gate is actually this time will be low. But the point is that even if we bring that low, it's not going to affect this part of the circuit because this is an AND gate. And for AND gate to be outputting, let's say 1, we need both of inputs to go high. So at this moment, we're just basically setting another line to low. However, if you look at that low line, it goes to our binary counter here, or count down basically binary counter here. Therefore, it's going to actually activate this circuit. So the value is already set as 10. So as soon as this line goes low, this value comes to the chip, and the output here immediately will be high because this is just the specification of this chip. As soon as you load the data, again, as I said, we are doing a countdown operation. So as soon as you load the data, it brings the TCD or countdown line high, right? And therefore, basically it waits for the clock pulse to receive and start counting down. However, immediately the TCD will be high. Therefore, that TCD, as you can see, come back here, and now we have a high signal. Now, at this stage, the circuit will be kind of frozen, and basically two major changes happened here. One, we are latching a high signal here, right? And also, we are setting that pin to high. But at this point, nothing else is going to happen. So that means that as soon as you actually set the TO signal high, two important latches are going to happen here, or one latch and one high signal. First, we're going to latch a high here, and second, we're going to set that signal to high. But still, our counter is not active because this AND gate is still not active, right? Okay, so again, when actually the signal goes high this time around, then those signals are going to transition. So that's going to go from high to low, and basically, regardless of our TO signal, the output of this signal will transition to high, and the next one to low, and finally the next one to high. So the circuit kind of reset itself to the ideal state up to exactly this point. But this point still remains high. All right, it kind of latched it. All right, so let's move on to the next stage. And I know it's becoming a little bit confusing, but bear with me. I'm going to summarize everything shortly. But the final stage is actually receiving the first bit on our RX line. And as you know, the first bit is actually a start bit, and it's supposed to be a low bit. All right. So just copying the same states from the previous slide, this line is actually, doesn't matter at this point, because when the RX line goes low, right? Let's say that we receive the first bit, which is the start bit, and that's how we detect actually the first bit in the circuit. When this line goes low, it immediately puts a high on the output, and now we are in business, right? Because we had that signal previously latched to high, and with the arrival of the first bit, we set that output to high. So this AND gate here will be outputting 1, which basically means that I think this is wrong here. This is actually should be high. I'm sorry about that. So imagine that this is a high signal, not low. So high comes in, and now we have a high signal on the master reset. And basically, finally, this chip will be counting. So when this chip is counting, as I said, it's going to be outputting one signal per each 16 signal or 16 clock pulses that comes to the chip. So let's say that first, 16 clock pulses came in, and then this line goes high. So when this line goes high, that means that actually our countdown chip will start counting. And now, since our first value was 10, it's going to reduce by 1, and it's going to be at level 9 or value 9. However, as I said, this line will be kept high until that reaches 0. So at 9, it's still high, so the clock circuit is active. and it continues the count down until it reaches 0. So that means that this chip will be counting from 10 to 0 for 10 consecutive values, and therefore the whole circuit will be active for exactly 160 clock pulses. So as you can see, this chip will be actually only outputting 10 clock pulses. The reason being is that this chip will be counting down all the time when this chip is active. And therefore, once this guy reaches 0, essentially it shut down the upper circuit, right? But we still, generated 10 clock pulses, and that's all we need. So those 10 clock pulses, as you can see, come to our serial to parallel shift registers here, and that's exactly what we need. 10 clock pulses to put all the 10 bits on the output. And once that output is actually put on the output lines of those shift registers, then our transceiver is ready to output them out. And that's exactly what is happening here. Now, if you actually follow again these states after this guy set to 0 or low, then the state of all of those can be resetted to what we have seen in the idle state. All right. So that means that we are actually kind of resetting the circuit back to idle, and basically we'll be ready to repeat the operation. So again, to be honest, I tried my best here to explain the circuit, but this circuit is relatively complex and there are a lot of lows and highs. But using these 3 slides, you could go through it probably on your own time and figure out exactly how the circuit works. Now, in summary, let me just give you a very quick summary so that if you really don't care about the details of every signal and every high and low, what is happening here. So, as I said, the circuit gonna go through 3 transition states. One is ideal, which we are not, receiving any data. The second stage would be when we set the TO to high, and that basically prepares the circuit for receiving the data. Again, at this moment, at stage 2, which was here, we are not actually receiving the data yet. We are just preparing the circuit to receive the data, and that means that we are latching that high here, and we are outputting high here at this moment. However, the last stage, when we actually receive the bits on the RX line, and since the first bit that we are receiving is a low bit, that means that we're actually activating the clock or the clock divider, and obviously the countdown circuit below it, and we're going to run the circuit in the middle exactly for 10 cycles, which means that we're going to need 160 clock pulse, original clock pulse on the clock divider, but we will be processing that for 10 bits, and as soon as we got to 10 bits, then this countdown circuit is going to turn the clock divider off, and therefore we only receive exactly 10 bits on the serial inline. And once we had the data here, essentially we just need to output it, which is basically happening by setting that output line, chip enable line low, and the data will be put on the bus. Alright guys, I hope that you guys got an idea in general how the circuit works. However, as I mentioned, probably you need to go through different stages by yourself and look at the signals and see what exactly happens. But I try to give you a general overview of the whole circuit. So in a nutshell, if we want to really receive the data on the circuit, we really need to bring the TO line high, and with the first bit received on the data stream or on the serial stream of bits, we will basically activate that circuit and receive the data and kind of reset the whole circuit back to idle and wait for the next bit to receive. I guess that was all about the circuit, so let's move on and test the circuit. Probably when we go through the sketches and testing, hopefully it will be more clear on how the circuit works. All right, let's go ahead and test it.
All right, so we're ready to test the RX module. In this test, we're going to use B register. Therefore, I'm going to actually mount the module which has the A and B registers and, of course, the ILE on it. So let me mount that module to our Arduino Mega Shield. And after that, I'm going to mount our UART module. So that's going to go on top of it. And finally, we are going to mount our LED board. All right. And just like the previous video, we need to connect both the USBs for the USB to serial adapter and also for Arduino Mega. So first I'm going to connect the USB cable for the adapter, and that's going to provide power and serial communication. And finally, I'm going to connect the USB port for our Arduino Mega Shield. All right, so now we're ready to test the module. Let's go ahead and have a look at the sketch, and we're going to come back to LED board shortly.
All right, so just like the previous video that we test the TX module, now I have opened the sketch on the left-hand side of the screen, and I have my terminal screen on the right-hand side of the screen. So this sketch is also quite simple. Let's have a quick look at the functions and see what we have here. So we start the function again with a main setup function, as you can see here on the screen. And basically I'm resetting all the pins as usual to put everything back to default. And then what I'm doing here is I'm setting all the bus pins to input. And the reason being is that once we send the data from terminal to Bravo, the data is going to show up on the bus of the Bravo. So we are basically going to read that data and we're going to do something about it. So obviously the bus pins should be set as input. Therefore, we have this line of code here. Now, we talked about the tone function in the previous video, and as I mentioned before, this is really just a function to create clock pulses on a specific pin. And here we have the clock pin. And as you can see, I'm creating 4,800 clock pulses per second. Now, the difference between this module and the previous one is that in this test, we are going to actually run the clock a little bit slower. As you can see, I picked the 4,800 clock pulses per second. And the reason being is that we want to actually go a little bit slow to see all the functions and be able to actually pick up the data from the bus and so on. So if this is the case and we are actually running the main module, or let's say the main clock on Bravo is set to 4,800 basically clocks per second, then we need to obviously readjust our serial basically application here. So we're going to go to setup, and in the serial port configuration, as you can see, I've selected the baud rate at 300 bits per second. So make sure that you match those. You know, whatever speed you're setting in your sketch should be divided by 16, and that's going to be our baud rate, which has been set here. Now, after that, the only thing that I'm doing in the setup function is really bringing the TO line high. And going back to the circuit logic, you remember that we talked about that signal, which basically, if we bring it high, it could prepare our RX module to receive the data, right? We said that we went through 3 different stages during circuit logic review, and I said that let's say in stage 2, basically we just bring that TO line high so that the circuit is ready to receive the data. And essentially with bringing that signal high, you would kind of latching a high signal here, if you remember, and also we were actually setting the TCD line high here so that it will be ready to receive the data. And obviously when the data is received on the RX line, with the first bit of the data that is received, it's going to activate basically our clock chips here, and it's going to receive the data in our circuit. So with that, what I'm doing here is I'm just bringing that TO line high, and actually I'm not taking it down during the test. The reason being is that we are not really trying to mimic the exact operation of our UART module in a final build. What we are trying to do is really just test the module. So I'm just going to keep that signal high because, I mean, we could probably bring it low at some point, but eventually we have to come back and bring it high because we need to prepare the circuit for the next character and so on. So I'm just simply bringing it high and keeping it high at this point. And as you can see, I'm not actually calling any other functions from the main setup function. So what I'm doing here instead, I'm actually using the loop function or the main loop function in our Arduino sketch. And I'm calling upon a specific function here, which called check receive. And reason being is that once we prepared the circuit to receive the data by bringing out the TO line or bringing the TO high, then at this point we should actually wait for the data to be received. And when the data is received on Bravo, then it's going to go through that circuit, and eventually the data is actually going to show up on our bus lines, right? So let's say that we prepare the circuit, the data is sent, it is coming from the RX line, the first bit or the start bit has been received, the circuit is getting activated, and eventually when that happens, that data is actually going to show up on our bus lines in Bravo. So one way to actually see if we have received any data is to check our bus lines, and that's what we're doing here. So essentially, we have to actually do that continuously, and that's why I'm checking that bus lines through that check receive function, as you can see here, and I'm calling it in the main loop function in our sketch. That means that this function is continuously called, and basically it's like a forever loop that is running here. Now let's have a look at the check receive function and see what it does. This one is quite simple again. So what I'm doing here is that first of all, I'm gonna basically read the bus lines, right? So I'm trying to see if any data has been received on the bus lines, and we actually have any data on the bus. That's why I'm creating a variable here called bus value, and I'm reading the bus. And you should be probably quite familiar with this function because we have used it in the previous videos and sketches. Read bus is just a function, simple function that goes through bus pins one by one and pull up the data, whatever data is on the bus, and basically it returns the data as an integer or as a variable. So we are basically just reading the bus, and we're checking if that value on the bus is actually 0 or not. So if nothing is sent and there is really no data on, let's say, on our receive line, therefore our bus will be set to 0 because there is no data on it. However, if anything has been sent through UART, then that data is going to show up on our bus, and that's basically what I'm doing here. I'm checking that value that we read from the bus to see if it's a 0 or not. So if it's not a 0, that means that we actually have a value on the bus, and at that moment what I'm doing is I'm actually turning off the main clock for the whole system. The reason being is that if you don't stop the clock, at least for this test, we would not be able to basically read that value on the bus and put it on the B register. And you may ask why we're gonna put it on B register. Well, the point is that that data is actually sent by our terminal to Bravo, and if you do not capture that data, it is just going to basically go on the bus, and then it's going to disappear, essentially with the next data that is coming in. So what we're trying to do here is really to read that data from the bus and kind of save it to one of our registers. In this case, I just picked B register, but you could pick A register or whatever you want. However, as I said, we have to stop the clock at that moment that we see the data on the bus, and then basically read that value into our B register. And if you remember from the module for A and B register, to basically read data into our B register, the only thing that we need to do is basically bring the BI line, or let's say underline BI line low, because this is an active low basically pin, and then pause the clock, right? So doing so would result in the data which is on the bus to be read into our B register. So I'm stopping the main clock on the computer, I'm just reading that value, and I'm pausing the clock, and that basically means that we're saving that value into B register. And after that, I'm just gonna, put the clock back where it was. So I'm gonna activating the clock again at the same rate that we had. And finally, we have a function here called transmit, which I'm gonna talk about that shortly. But for now, I'm gonna basically just, comment that out because we wanna just test this part that I explained. Well, another thing that I have to mention here is that, as you can see, I'm using actually a pause clock here function, and this is the same pause clock function that we were using in the initial videos. And basically what it does is just bring the clock line or clock pin high, wait for a delay, and bring it low, and again wait for a delay. So it's going to create a single clock pulse, and that's what we need here to read the data into B register, because our main clock pulse is turned off in the previous line. So we need a single clock pulse here, and that's how we generate it so that we could read that data into B register. All right, so with that, what is the expectation? With that, we expect that when we actually send the data to Bravo, that data should be captured by this part of the code, and eventually it should show up on our B register. All right, so let's go ahead and basically upload this to our Arduino and see what will happen. So I'm gonna save, I'm gonna test it. Finally, I'm gonna upload it. All right, looks like it has been uploaded. However, as you can see, I'm reading actually 255. I'm not sure where this actually data is coming from, but let's go ahead and type something on the screen and see what will happen, see if you can actually send any data. So I'm gonna actually press character A, and as you can see, nothing is happening on the screen here, on the terminal screen. It's just the cursor is blinking. However, when I pressed character A on the keyboard, you see that we actually have a value here on the B register. So I'm going to continue pressing a couple of more characters like B, like C, like D, E, F, and so on. So as you can see, although you can't see my keyboard, but I'm actually typing on the keyboard. However, you don't see anything on the terminal screen, it's just blinking. But when we actually enter a character, it looks like that Bravo is actually receiving this character and is gonna put it into our B register. So that's cool, but why we are not seeing the character on the terminal? Well, the point is that that's actually a property of the terminal, not this terminal, just any other terminal, that a terminal is not like a text editor that you could type something on it and see it. A terminal is just basically a program that takes the input and send it over to the other side. And again, the same thing is happening. So in fact, if we really want to see what we are typing on the screen, with most of the terminals, we have to do an echo. An echo means that when we are sending a character, basically through terminal, the other side should echo it back to us, and this way we'll be able to see it on the screen. So in order to echo that character back, what we could do here, we could basically use the transmit function that we talked about in the previous video. So we know that we already built a transmit module in the previous video, and we know how it works. And if you remember, we actually had a transmit function. We could use the same function with a little modification, and that's what we have here on the screen. So as you can see in the transmit function, what I'm doing is I'm bringing the BO line low, which is the basically B register out low. Again, this is an active low signal. So by bringing this line low, we are going to put the content of the B register on the bus again. And once I'm doing it, I'm basically bringing the TI line high. And if you remember from the previous video in transmit module, the TI line is the line that the control signal that we are actually using to send or transmit data from Bravo. So by doing so, I'm just putting the content of the B register on the bus, and then I'm gonna basically transmit that. I'm gonna send it out from Bravo side. And I'm gonna wait for a short delay, and I'm gonna reverse those signals back, basically meaning that TI will be low and BO line will be high. So the expectation here is once we actually went through this part, which basically sends the data from the terminal to Bravo, eventually we're gonna actually echo it back from Bravo side, meaning that we read the B register to the bus, and then we're gonna send it out back to our terminal. So it's like sending a character and echoing it back again to the terminal. So this way, we actually would be able to see the character that we just sent to Bravo, and that's gonna test both sides, right? That's gonna test send and receive. All right, so that's actually the last part. So let's do it and see what will happen. I'm gonna check again, and I'm gonna upload it to Bravo. Okay, so let's type something this time. So we're gonna say, well, as you can see, as soon as I'm typing T, it's actually gonna transfer to Bravo. So as you can see, it's gonna actually show up on our B register here. And also, I'm getting the character T on the screen, which means that Bravo actually sent that character back to us and kind of echo it back, and that's why we're going to see it. So let's type something. So this is a test, right? And that's it. That's how you really could communicate with Bravo. You can send and receive data. And how cool is that? Right? And as you can see, when I'm typing, actually, all of those characters are going to get into B register one by one. So this is very cool. So at this point, I guess we tested both, the send and receive operation in our UART module. And of course, as you can see, all other characters like enter, like backspace, and all of those are actually supported because now we're actually sending and receiving the character into UART standard, and it's going to understand it on both sides. And now the only thing that remains here is that if I actually type really fast, if I let's say push the B character on the keyboard really fast, as you can see, I'm gonna get actually some special character or gibberish on the screen. And the reason for that is, as you can see, we are actually running the clock at the lower speeds. And basically what is happening here is that if you're sending characters too fast to Bravo, there will not be enough time for Bravo to process those characters. And if you remember from the circuit when I was explaining it, we needed 160 clock pulses for each stream of data, for each frame that is coming to Bravo. So essentially, if you're actually typing a little bit faster than that, meaning that if you're timing between the characters that you're sending to Bravo is actually faster than 160 clock pulses in between them, then obviously those characters are not going to be fully received, and we're not going to see the character on the bus, or the correct character on the bus. Therefore, what you see here is that just the result of kind of lower speeds on the clock. And this is not going to be an issue because obviously in final version, we're going to run the whole computer at much higher speed. So you're probably never going to see that. And another thing that I would like to mention here is the fact that when we are sending those characters to Bravo, And at this point, we are just, saving them immediately into a B register. However, if you think about it later when we are actually, let's say, writing a command or some code on the screen and we want to send that, that code or command consists of multiple characters. Therefore, at that point, we actually need a way to save those characters somewhere else on the memory so that we could basically go back to them and process them and see, okay, what command actually has been sent, right? So for example, in the future, when let's say you develop a small operating system, or let's say an assembly or something like that. So if you, for example, say LDA, let's say 15, and you want basically load a register into memory address 15, what is happening here is you're sending multiple characters here, as you can see on the screen, and that basically needs to be somehow processed, and that's when the stack operation comes into play. And basically with any character that you're sending from terminal, you have to actually save it in a memory space, and then you're gonna refer back to that, and you're gonna basically process that, what character is that, and then combine those and basically say what is the meaning of those stream of characters that I received. So this is what's gonna happen eventually, but for now I just wanted to show you the operation of the UART module and basically how the data is actually exchanged between Bravo and a serial terminal in a simple way. So I hope that you guys have enjoyed this video and were able to understand a little bit more about the UART module. With that, we're going to conclude this video. In next video, we're going to look at our control logic, which would be more about writing microcode and how that could actually generate our control signals and send it to different modules in Bravo. All right, see you guys later in next video.